Again, we can use common sense to think about temperature. If I increase the temperature of a reaction, what happens to the rate? It gets quicker, doesn't it? Yeah, we know that. Yeah, that's okay. Why is that the case? Well, if I increase the temperature, what happens to the particles? Speed. Yeah, they've got more kinetic energy, they move faster. If they are moving faster, they're going to more likely collide. So, again, thinking of you guys in your room, like so, with a mixture, I can put boys in here as well, all moving randomly. If you all start running around, you're more likely to collide, aren't you? If you're just like this, you're not going to collide very often. But if you start going into a frenzy of activity, you'll probably seriously hurt yourselves. However, you will more likely to collide with another particle. So that's one reason. However, there's another reason. You'll collide more often, but we say because you've got more energy, you're more likely to react. If you think about atoms, if you think about an atom or a molecule, what surrounds them? Electrons. If I've got two atoms colliding together, what's going to meet? The two electron clouds, which are negative. Yeah? What do two negative things tend to do? Yeah, they're going to bounce. So most of the time, atoms just bounce off each other. So, when we go back to this, if you just knocked in, you'd knock in, and then you just wander off again. However, if you were going at speed, not only will you collide more often, but there'll be more successful collision. You're more likely to meet them, which kind of makes sense. If you just knock into someone and go, sorry, walk away. Okay, if you really whack into them, you're more likely to start a conversation with them, aren't you? Because you're going to have to apologise at least. So, they're more successful, and if you start talking, you're more likely to actually move it on. Okay, so not only are you colliding more often, but we have to say there are more successful collisions per second. That's the key thing to talk about. Increasing the temperature increases the kinetic energy of the particles. This means they move faster and collide more often. However, because they have more energy, when they collide, they are more likely to react together. So, there are more successful collisions per second. So that's key. There are more successful collisions per second. Well, not only are there more collisions, but more of them are successful as well. So it's a double whammy effect. So when you look at temperature, increasing temperature has a massive effect on rate of reaction, far more than increasing concentration. There's a special name for this. Particles need a minimum amount of energy for them to react. So we said they're colliding more often and they're more successful. Most of the time they react, they hit each other and they just knock off, they don't react. What we say is in order for them to have a successful collision, they have to have a minimum energy, and that energy is called the activation energy. If they haven't got that activation energy, if they haven't reached that threshold of having activation energy, the collision is not successful and they just bounce off each other and go their separate ways. If they do have this activation energy, then we have a successful collision. So before we move on, we're just going to do a little bit about activation energy, which is that minimum energy. The activation energy is the minimum energy, the minimum amount of energy needed for particles to react. If they don't have that energy, nothing happens. So we're going to go back to what we were doing in our last topic, enthalpy profile diagrams. So if I go back, and hopefully you remember this, remember we had enthalpy along here, and along this axis we had reaction coordinate. So for an exothermic, we had our reactants here, and we had our products here, and we said that was delta H, which was negative. It was delta H that we were measuring in our last topic. What I'm going to add on in red is another line which shows the activation. It's like a hill. So my reactants don't just go reactants down to products. They have to go over this hump, like so. And that, in red, is my activation energy, which is called EA. So that is my activation energy. So they have to get over this energy barrier. If they can't get over that energy barrier, they just go back into their reactants again. So that's my activation. If they successfully do it, they get to my products. But if they don't, so that's delta H is what we measured last unit. Activation energy is something that we're talking about in this topic. For a endothermic reaction, it's very similar, apart from the fact that now my products have more energy than my reactants. So that is delta H. If I put my activation energy on, that there is my activation energy in red. Again, notice single-headed arrows. Please don't put double-headed arrows on. So that is what we measured that for my endothermic, and that would be a positive figure. And my activation energy